Hello class 12. In this video we're going to discuss some of the numericals from the topic interference of light. The reason that I'm holding the book is because I don't want to copy the question. Okay, so I'll read out the questions for you, listen to the question. Reading the question and understanding the question is very, very important. Okay, so it says the first question, this had come in ISC 2012. This had come in ISC 2012. It says, in Young's double slit experiment using monochromatic. Oh, by the way, in the video for interference of light, when we were discussing, I forgot to tell you that the source of light has to be monochromatic. Monochromatic meaning having a single frequency. For us to get, in Young's double slit experiment, for us to get alternate bright and dark fringes, their source of light has to be monochromatic. Remember, I forgot to mention that. Okay, that is one of the conditions. It has to be monochromatic. Okay, single frequency means that. Okay, same frequency. So in Young's double slit experiment using monochromatic light of wavelength 600 nanometers, so lambda is given to be 600 nanometers. Nanometers meaning 600 into 10 to the power minus 9 meters. Okay, you have to work in SI system of units. Interference pattern was obtained on a screen kept 1.5 meters away from the plane of the two slits. So to say, capital D is given to be 1.5 meters, the distance of the screen from the two slits. Calculate the distance between the two slits. We are to, so to say, find small d, the distance between the two slits. If fringe separation width or fringe width is found to be 1 millimeter. What is given is, beta is given, fringe width is given, 1 millimeters. 1 millimeters meaning 1 into 10 to the power minus 3 meters. So these are the things that are given, and we have to find small d, that is slit separation. Now how will we proceed? We know beta is lambda capital D by small d. Okay, so beta is given, lambda is given, capital D is given. You only need to find small d. Okay, so small d will be given by lambda capital D by beta. Lambda is given to be 600 into 10 to the power minus 9 meters. You have to work in the same system of unit. So 1.5 meters capital D is divided by beta is 10 to the power minus 3 meters. Okay, so this meter, they divide each other and D comes in meters. Okay, D you can calculate in millimeters also, you can convert it to millimeters. So use your calculator and it comes out to be, small d comes out to be 9 into 10 to the power minus 4 meters. Okay, very simple. You get this kind of simple numerical. Okay. So let me erase this. So this is numerical number 1. Let me give you another numerical. This had come in 2017, ISC 2017. It says, in Young's double slit experiment using monochromatic light of wavelength, again wavelength is given lambda 600 nanometers, which is, it's the same value that's given, 10 to the power minus 9 meters, remember. Fifth bright fringe is placed at distance of 0.48 millimeters from the center of the pattern. If you remember, if this was the screen, say at point P we have our fifth bright fringe, what the question is speaking about. This is the central point O. Okay, so this distance we have taken it to be x. The distance at point P, any random point P for now, any random point P from point O, our central position on the screen, was x. Now if our bright fringe, fifth bright fringe, as the question is saying, if our fifth bright fringe happens to be at point P, okay, then we know x is given by the position of the fifth bright fringe is given by 5 lambda capital D by small d. this is the equation, or the value for the fifth. The value of x is given to be 0.48 millimeters. 0.48 mm. So 0.48 mm is this much. This is what is given. Because from the condition for bright fringes, nth bright fringe, the position for nth bright fringe is this. Okay, alright. So this is the fifth bright fringe. For now, the value of n is 5. Okay, so that is given to be 0.48 millimeters. If the screen is at a distance of 80 centimeters, D is at 80 centimeters, meaning 0.8 meters. Calculate, you need to find two things: the distance between the two slits, this is to be calculated, and the fringe width, beta, is to be calculated. Alright, so what would you like to calculate first? If you see, beta is simply lambda capital D by small d. So from this equation, so 5 lambda capital D by small d is 0.48 mm. From dividing this by 5, you will get lambda d by d. You can find the fringe width there. Okay, and slit separation, small d, lambda is given, capital D is given. Okay, so you can find slit separation also from here. Okay, what can you do? Well, so let us first find the fringe width. Fringe width will be beta, will be lambda capital D by small d. Okay, I'm being very disorganized. Okay, I hope you all understand, but still you all understand, I hope. This divided by 5 is going to give us the fringe width. 0.48 divided by 5. This comes out to be 0.096 mm. Okay, so that is the fringe width. Now once you've got your fringe width is 0.096 mm. This is a fringe width. Now once you've got your fringe width, so this is lambda capital D by small d. Now we need to find small d. Small d will be, lambda is given 610 to the power, okay, let me first write this. Small d will be lambda capital D by your fringe width. I hope you all are following. Okay, so small d is 600 into 10 to the power minus 9 meters into 0.8 meters divided by 0.096 mm is 96 into 10 to the power minus 5 meters. Why? Because this is equal to 0.096 mm is 0.096 into 10 to the power minus 3 meters, okay, which can be written as 96 into 1, 2, sorry, this is 10 to the minus 6. So 1, 2, 3. So 96 into 10 to the power minus 6 meters. Okay, so once you do the calculation, you will get small d to be 5 into 10 to the power minus 3. So small d comes out to be 5 into 10 to the power minus 3 meters. So 10 to the power minus 6, 10 to the power minus 9, this will give you 10 to the power minus 3 already. Okay, so when you do the calculation for 600, 0.8 and 96, it comes out to be 5. Alright, so this will come in ISA 2017. And let me do one more. You get this kind of questions only. Okay, you get this kind of numericals only. So when I erase 2007, ISC 2007. So this will be the last question, okay? Last numerical that we discussed. This is a bit different, okay, but still the same. The distance between first and sixth bright fringes. So this is your central map. So this is the first bright fringe, okay. So and your sixth bright fringe is somewhere over here. All right. So this distance, this is your sixth bright fringe. This is the first bright fringe. So the distance between the first and the sixth bright fringe is given. In Young's double slit experiment is 12.5 mm. Now, the formula for the equation for nth right fringe is xn is n lambda capital D by small d. So the distance of the sixth, this is what the distance of the nth right fringe from point O, the central maximum, so to say. So the position of the sixth right fringe from the central maximum will be 6 lambda d by small d, and the position of the first right fringe from the central maximum will be lambda capital D by small d, simply from this equation. So what the question has given us is the distance between the first right fringe and the sixth right fringe, okay, which is 5 lambda d by small d. This minus this gives us 5 lambda d by small d. So this is given to be 12.5 mm, which is 12.5 into 10 to the power minus 3 meters. This is given. Okay, and furthermore, the question, so understanding the question is very, very important, remember. Otherwise, you get very simple kind of numericals from interference and also diffraction. We'll discuss about that. Small d is given to be slit separation is 0.12 mm, which is 12 into 10 to the power minus 3 meters. And the distance of the screen from the slit, so capital D, the distance of the screen from the slit is 60 centimeters, which is 0.6 meters. Okay, so it says calculate fringe width, we need to calculate beta, and we need to find lambda also, the wavelength of light also we need to find. Okay, so from this equation itself, lambda capital D by small d is a fringe width. Okay, so fringe width beta is 12.5 into 10 to the power minus 3 meters divided by 5 gives you beta. So beta comes out to be 2.5 into 10 to the power minus 3 meters. So that is your fringe width. 2.5 into 10 to the minus 3 meters is a fringe width. And the question also asks us to find lambda. Now again, beta is lambda capital D by small d. We know this. So lambda will be what? Beta small d by capital D. Beta we've just now found out. So 2.5 into 10 to the power minus 3 meters into slit separation 12 into 10 to the minus 3. Only thing is my space. So 12.5 into 10 to the power minus 3 into 12 into 10 to the power minus 3. 12 into 10 to the power minus 3 meters again, divided by capital D, which is 0.6. So 0.6. Okay, so this is 0.1 and 2. 0 for 5 to 225 into 10 to the power. Lambda should come out to be, have I made some mistake? 12.5. Beta is 2.5. My beta is different. Yeah, that is what I made a mistake over here. The value of beta. Okay, beta is 2.5. I substituted 12.5. It should be 2.5. And it comes out to be 50 into 10 to the power minus 336, 10 to minus, minus 1, 10 to minus 7, 500 into 10 to minus 7 meters. Okay, check the mathematics, you can check the mathematics, but I hope the physics part is clear. Okay, so this is the formula that you need to remember. Okay, this also gives us the formula for the fringe width, which is this, beta is lambda d by small d. Okay, so you substitute the values, check the mathematics, and you can work out the mathematics yourself.